On November 8, 2021, at 14:47 UTC, every seismic sensor in the Lunar Monitoring Network registered a simultaneous event, all 40 of them, spread across both hemispheres, near side and far side, poles and equator. 40 independent instruments, each one planted in a different location, each one recording independently, each one sending its data to our station through a separate tight beam relay. All 40 registered the same signal at the same moment. Not an impact. The waveform was wrong for an impact. Not a moonquake. The depth signature was wrong. The frequency was wrong. The duration was wrong. This was a displacement. A single, massive lateral shift originating from a point approximately 740 kilometers beneath the lunar surface. Below the crust, below the upper mantle. Deep in the interior, where the standard models say there is nothing but iron and nickel and the slow, dead cooling of a body that hasn't been geologically active for 3 billion years. Something that the instruments measured at roughly the volume of Lake Superior changed position by approximately 200 meters in 1 second, and then stopped. No aftershock, no resonance, no secondary activity. Just a single movement and then stillness, like something rolling over in its sleep. I was in the sensor operations bay when it happened. I'd been monitoring the network for 9 months. In 9 months, the most exciting thing the sensors had recorded was a magnitude 2.1 shallow moonquake caused by thermal stress fracturing. This was not that. This was something else entirely. I stared at the waveforms on 40 screens and I understood, with the calm clarity that comes when your expertise is suddenly violently relevant, that the moon had just done something it wasn't supposed to be able to do. The Apollo 12 crew reported in 1969 that when they deliberately crashed their lunar module ascent stage into the surface, the moon rang like a bell. The seismometers they'd planted recorded reverberations that lasted for nearly an hour. The moon vibrated as a unit, the entire body resonating, the way a bell resonates when struck. NASA published the data. Scientists proposed explanations: the dry, fractured regolith transmitting seismic waves with unusual efficiency, the lack of water dampening, the particular composition of the lunar crust. Reasonable explanations. None of them fully accounted for the duration or the coherence of the ringing. The moon rang for 55 minutes. No natural rocky body should ring like that, but a hollow one would. I can explain why the moon rang like a bell. Bells are hollow. Sentinel Station was not in any database that a civilian could access. It didn't appear in the DoD budget. It didn't appear in NASA's manifest. The orbital tracking networks listed it as a defunct environmental monitoring satellite, decommissioned in 2028, tumbling, inert, scheduled for eventual deorbit. In reality, it was a 4-module classified platform in a 110-kilometer polar lunar orbit, crewed continuously since 2027 by 4-person teams on 12-month rotations. My team was the 5th. The station had one purpose: to operate and monitor a network of 40 seismic, gravimetric, and thermal sensors planted on the lunar surface between 2026 and 2029. The sensors had been delivered by unmanned landers launched under cover of commercial payload contracts. The landers were listed as technology demonstrators. The sensors were listed as geological survey equipment. Both of these things were technically true. The technology being demonstrated was the ability to secretly instrument an entire celestial body. The geological survey was of the moon's deep interior, and the results of that survey had been classified before the first sensor powered on. The crew was 4. Commander Vasquez, military intelligence background, tight-lipped in a way that went beyond professional discretion into something more personal. She knew things about the program's history that the rest of us didn't, and the weight of that knowledge was visible in the careful way she chose her words. Ose, gravimetric analyst, des data from Darn. Responsible for the mass distribution data, a quiet Ghanaian with a PhD from Caltech and a gift for making incomprehensible mathematics feel intuitive. Park, communications and data security, managed the encrypted uplink to Earth Command, the only pipeline through which our data left the station. And me, Wainwright, seismology. My job was the waveforms, reading the vibrations of the moon the way a cardiologist reads the rhythms of a heart. For 9 months, the moon's heart was still. The sensors recorded the baseline, thermal moonquakes, shallow, predictable, caused by the 300-degree temperature swing between lunar day and night. The occasional deep moonquake, rare, faint, originating from around 700 to 900 kilometers depth, caused by tidal stresses from Earth's gravity. And beneath it all, like a foundation note in a chord nobody was playing, is the anomaly. The persistent low-frequency signal that the sensors had been recording since they powered on in 2026. It sat at the bottom of the frequency spectrum, below the moonquakes, below the thermal noise, below everything. A drone. Constant, unchanging, not oscillating, not pulsing, just there. Like a vibration in the walls of a building that you can't trace to any specific source. The first crew cataloged it as geological. The second crew cataloged it as geological. The third and fourth crews cataloged it as geological. I cataloged it as geological because that's what you do with low-frequency seismic noise from a body that has no tectonic activity. You call it residual cooling. You call it tidal deformation. You call it background. You don't call it what it actually sounded like, which was something humming. The station orbited the moon every 118 minutes. Every 118 minutes we passed over the full surface, day side and night side, near side and far side. The cupola, the small observation dome on the station's underside, faced the moon directly. You could look down through it and watch the surface pass. The craters, the Maria, the rills, the highlands, gray, silent, dead. A world that had never been alive, that had never had an atmosphere or an ocean or a single cell of biology. A rock, a companion to Earth for 4.5 billion years, familiar, predictable, the most studied object in the sky. I looked down at it every orbit for 9 months, and every orbit I had the same thought that every astronaut who has ever orbited the moon has had. It's bigger than you think. From Earth, the moon is a disk, a circle in the sky, small enough to cover with your thumb. From 110 kilometers, it's a world, a landscape. It fills your field of vision. The craters have depth, the shadows have weight. You can see the curvature of the horizon, and the horizon is close. The moon is small enough that the surface curves visibly at this altitude. You're not above a planet, you're above a sphere, and the sphere is wrapped around something. The monitoring program had a history that I was given access to in fragments. My clearance covered the seismic data and the sensor operations. Vasquez had a higher clearance. She had access to something called the archive, a data set that predated the program, that predated the station, that went back to 1969. The Apollo Passive Seismic Experiment, 5 seismometers planted by Apollo missions 11, 12, 14, 15, and 16. They operated from 1969 to 1977, recording the moon's seismic activity for 8 years. The data was public, published, analyzed, discussed in hundreds of papers. The Bell phenomenon, the deep moonquakes, the thermal events, all public. But the archive, Vasquez told me once, late at night in the cupola, the moon sliding beneath us in the dark, contained data that had never been published. Signals from the Apollo instruments that had been recorded, transmitted to Houston, reviewed, and then removed from the public dataset before release. She said this carefully, without elaboration, the way a person shares a secret they've been carrying too long. I asked her what the signals showed. She said, "The same thing ours show." She didn't say what that was. I didn't press. I had my own anomalies to manage, the density discrepancy. And it had been in the literature for decades, not classified, not hidden, just quietly unresolved. The moon's density is 3.34 grams per cubic centimeter. Based on its size and estimated composition, iron-nickel core, silicate mantle, basaltic crust, the density should be higher. Not dramatically, but measurably. The moon is about 2% less dense than the models predict. The standard explanation involves a smaller than expected iron core. The moon formed from debris ejected by a giant impact on early Earth, the prevailing theory, and the debris was disproportionately mantle material, lighter, less iron. Reasonable. But the seismic data from the deep interior didn't support a small iron core. The seismic wave propagation below 740 kilometers was anomalous. BP waves and S waves, the two types of seismic waves that propagate through solid material, behaved unexpectedly at depth. The P waves slowed more than predicted. The S waves attenuated sharply, losing energy, weakening, as if passing through material that wasn't fully solid. The standard interpretation: the deep interior contains a partially molten zone. Reasonable. Every model of the lunar interior included a partially molten boundary layer at approximately 700 to 800 kilometers depth, but partially molten rock has a specific seismic signature: gradual velocity reduction, frequency-dependent attenuation, scattering. What our sensors showed wasn't gradual, it was sharp. The seismic properties changed at 740 kilometers like a switch being thrown. Above 740 kilometers, normal lunar geology. Below 740 kilometers, something else, a different material, a different density, a different response to seismic energy. I brought this to Vasquez in month 3. I showed her the velocity profiles, the attenuation data, the sharpness of the 740-kilometer boundary. I told her it didn't look geological. She looked at my data for a long time. Then she asked if I'd read the Apollo PSE data on the deep moonquakes, the original data, the published version. I said yes. She asked if I'd noticed that the deep moonquakes all originate from the same depth range, 700 to 900 kilometers. I said yes, I'd noticed. She asked if I'd wondered why. I said the standard explanation was tidal stress concentration at the core mantle boundary. She said, "There is no core mantle boundary, not the kind the textbooks describe." I asked her what she meant. She said, "Keep monitoring, you'll see." There was one more thing: the 118-minute orbital period. I noticed it in month 4. The persistent low-frequency anomaly, the drone, the background hum from the deep interior, had a subtle modulation, a cyclic variation in amplitude that repeated every 118 minutes. Exactly. The same period as our orbit. I assumed it was an artifact, some interaction between the station's orbital mechanics and the sensor relay timing. I ran the correlation analysis and eliminated the orbital artifact. The modulation remained. The deep interior of the moon was pulsing in a cycle that matched our orbital period. Or, a thought I didn't follow to its conclusion at the time, our orbit matched the moon's pulse. The station had been placed in a 118-minute orbit because that orbit matched something already happening inside the moon. We weren't observing a coincidence, we were synchronized. November 8th. I was in the sensor ops bay at 1445 UTC, running the daily calibration check on the network. Routine. The 40 sensor indicators green on the board, the waveforms scrolling at their baseline levels, the seismograph printers ticking out paper at 25 millimeters per second. At 1447, every waveform on every display jumped. I don't mean spiked, I mean jumped. The traces, which had been sitting at baseline for 9 months, shot to the top of their scales simultaneously. All 40. The seismograph printers lurched, the pens slamming to their limits, the paper advancing as the instruments struggled to keep up with the amplitude. The alarm system activated. Not the moonquake alarm, a different alarm, one I'd never heard before. A classification level alert that triggered automatically when the sensor network detected a deep interior event exceeding predefined parameters. Parameters I hadn't known existed. The waveform was like nothing in my experience. I'd spent 20 years reading seismographs, first on Earth, then on the moon. I knew what impacts looked like: sharp onset, exponential decay. I knew what moonquakes looked like: emergent onset, gradual build, P wave followed by S wave with a measurable delay corresponding to distance. This was neither. The onset was instantaneous, all 40 sensors registering the signal at the same moment, which meant the source was either equidistant from all 40 sensors simultaneously, which was geometrically impossible unless it was at the moon's center, or the signal propagated at near infinite velocity through the interior, which was physically impossible. The waveform itself was a single pulse, a sharp displacement followed by a complete stop. No decay, no oscillation, no ringing. The Moon, which had rung for 55 minutes when struck by a 2-ton ascent stage in 1969, absorbed this event in absolute silence. The energy went in and didn't come out. The source depth was 740 kilometers. Exactly. The 740-kilometer boundary I'd been studying for months, the sharp transition in seismic properties that I'd flagged to Vasquez. The event originated from that boundary, from the surface of whatever lay below it. I ran the source analysis. The algorithms took the data from all 40 sensors and triangulated the origin point, the magnitude, and the nature of the deformation. The results came back in 3 minutes. The event was a lateral displacement, not a fracture. The rock hadn't broken, not a tremor, nothing was vibrating. Something had moved. The instruments calculated the volume of the displaced material at approximately 12,000 cubic kilometers, roughly the volume of Lake Superior. The displacement distance was approximately 200 meters. The duration was approximately 1 second. 12,000 cubic kilometers of material, shifting 200 meters laterally in 1 second, at a depth where the standard model said there was nothing but slowly cooling iron. I sent the data to Earth Command at 1452 UTC. The light speed delay to Earth from our position was about 1.3 seconds, negligible. The response delay was not negligible. Earth Command did not respond for 4 hours when the response came, for it was 2 words from the program director. Confirmed. Continue. No questions, no requests for additional analysis, no expression of surprise. Confirmed. As if they'd been expecting it. As if the entire program, the secret sensors, the classified station, the 5 years of continuous monitoring, had been waiting for exactly this. I asked Vasquez what confirmed meant. She said it meant the event matched a predicted scenario in the program's contingency planning. I asked what scenario. She said, the one where something inside the moon wakes up. The pulse appeared 12 hours after the displacement. The seismic network detected it at 2:30 UTC on November 9th, a rhythmic signal originating from the same depth as the displacement, from the same coordinates, 0.008 Hertz, 1 cycle every 125 seconds, approximately 2 minutes. The waveform was clean, sinusoidal, a smooth, regular oscillation that looked nothing like any natural seismic process I had ever recorded on any body in the solar system. Geological processes produce noise, complex, broadband, chaotic. This was a pure tone, a single frequency, maintained with a precision that implied active regulation. Something was generating it, something with a rhythm. On November 11th, there was a second displacement, smaller than the first, 3,000 cubic kilometers, 80 meters, still at the 740-kilometer boundary, but at a different location. The first event had been centered beneath the Procellarum Basin on the near side. The second was beneath the South Pole Aitken Basin on the far side, opposite hemispheres. Whatever was moving inside the moon was not confined to one area. It occupied a volume large enough to reach from one side to the other. The gravimetric data confirmed it. Osei, our mass distribution specialist, ran the gravitational analysis on both displacement events and the ongoing pulse. His findings were delivered to the crew in a brief that lasted 40 minutes and left the room silent. The moon's gravitational field had changed, not in a way that was detectable from Earth. The perturbation was too small to affect the orbit or the tides. But from 110 kilometers, with instruments designed for exactly this purpose, the change was clear. The mass distribution inside the moon had shifted. Material that had been in one location for billions of years was now in a different location. The shift was not consistent with fluid dynamics, not magma movement, not convection. Not any process that involved liquid or semi-liquid material responding to pressure gradients. The shift was consistent with a solid body-changing position within a bounded space, an object repositioning itself inside a container. Osei used the word object carefully. He did not use the word organism. He didn't need to. The shape of the gravitational perturbation said it for him. The mass distribution change was asymmetric, elongated, one end denser than the other. It looked on the gravimetric model like a body with a head and a tail. I reported the pulse and the second displacement to Earth Command through the encrypted uplink. The response time, which had been 4 hours after the first event, was now 18 hours. When the response came, it wasn't from the program director. Indeed, it was from someone I'd never communicated with before. The classification was above the program director's level. The message was brief. All station personnel were to cease external communication effective immediately. All data was to be retained on station. No transmission of raw sensor data to any facility outside the classified network. The station was being isolated. We were alone with the data. That evening, Vasquez came to my station in the sensor ops bay. She was carrying a data tablet, not the standard issue station equipment, a personal device that she'd brought aboard and never shown anyone. She set it on my console and opened a file. The file was dated 1972. It contained seismic data from the Apollo 14 passive seismic experiment, but not the published data. Different waveforms, different time signatures. Recordings that had been made during the same period as the published data, but had never appeared in any public dataset. The recordings showed a signal. Low frequency, deep source, rhythmic, 0.008 Hertz, one cycle every 125 seconds, the same pulse, identical frequency, identical waveform, recorded by the Apollo 14 seismometer in 1972, 59 years before our sensors recorded it in 2021. I looked at Vasquez. She said, "The pulse has been there since we first listened, since Apollo. It stopped in 1977 when the last Apollo seismometer was turned off. Or," she paused, "we stopped listening and assumed it stopped. When our sensors came online in 2026, it was there. The same signal, the same frequency, unchanged, as if it had been continuing the entire time for 60 years with no one to hear it." I asked her why this had been classified. "Yeah," she said, "because the alternative to classifying it was admitting that the moon has a heartbeat, and nobody, not NASA, not the DoD, not any government on Earth, was prepared to explain to 8 billion people what that meant." The pulse continued. Every 125 seconds, through the walls of the station, through the vacuum between the station and the moon, through 110 kilometers of space and 740 kilometers of rock and whatever lay beyond the rock. A rhythm. Patient. Ancient. The heartbeat of something that had been beating since before the first human looked up at the night sky and saw a silver disk and called it the moon. November 15th. I built the model. 5 years of seismic tomography from 40 sensors. Every wave, every reflection, every refraction, every attenuation fed into a 3-dimensional reconstruction algorithm that I'd originally developed for imaging the Earth's inner core. The algorithm took the seismic data and constructed a density map of the lunar interior, layer by layer, from the surface to the center. I'd run partial versions before. Everyone on the program had. The standard reconstructions showed the textbook lunar interior. Crust, upper mantle, lower mantle, the anomalous boundary at 740 kilometers, and below that, the core, rendered as a uniform, slightly less dense region that the models labeled as partially molten iron nickel. What I did on November 15th was different. I ran the full dataset, not the filtered, processed standard model version that Earth Command received in the daily summaries. The raw data, every signal, every anomaly, every frequency, including the persistent low-frequency hum, including the pulse, including the displacement events. I removed the geological assumptions that the standard reconstruction imposed, the assumption that the interior was composed of rock and metal, the assumption that density variations followed mineralogical models, the assumption that the moon was a natural body with a conventional internal structure. I let the data speak for itself. The reconstruction took 40 minutes. I watched it build on the main display in the sensor ops bay, layer by layer, depth by depth, the moon's interior assembling itself out of pure seismic information. The outer layers were normal. Crust, 60 kilometers of anorthosite and basalt, exactly as expected. Upper mantle, olivine and pyroxene, density increasing with depth, standard compression gradient. Lower mantle, denser, the seismic velocities slowing as predicted by temperature and pressure models. Everything consistent with a natural body, a rock that had been doing rock things for 4.5 billion years, then 740 kilometers. I shared the reconstruction with the crew, not through the official reporting chain. Earth Command had isolated us and I no longer trusted the chain. I put it on the main display in the sensor ops bay and I called everyone in. Vasquez, Osei, Park. They stood in front of the screen and they looked at the shape in the center of the moon, and nobody spoke for a long time. Osei broke the silence. He said, "The density profile is biological." I said I knew. He said, "The segmentation pattern is consistent with a body plan. Arthropod. Or something with a similar structural logic. Repeated segments, bilateral symmetry, a tapered anterior, denser posterior." I said I knew. Vasquez said nothing. She was looking at the screen the way you look at something you've been told about but never seen, as if the shape on the display confirmed something she'd been carrying alone for years. Park said, "What do we tell Earth?" Vasquez said, "Nothing. Earth already knows." I asked her what she meant. She said the archive, the classified Apollo data, the unpublished recordings, the 60 years of institutional silence, existed because the evidence had been there since 1969. The Bell phenomenon, the anomalous density, the seismic velocity discontinuity at 740 kilometers, the persistent pulse, all of it had been detected, measured, analyzed, and buried by a classification program that spanned 11 administrations and 3 space agencies. Nobody had built a model as detailed as mine. The sensor network didn't exist until 2026, but they'd known. Since Apollo, they'd known that something was wrong with the moon's interior, and they'd spent 60 years not telling anyone. The organism. I need to describe what the seismic data showed, because the seismic data was the only way to see it. We couldn't photograph it, we couldn't sample it. It was 740 kilometers below the surface, sealed inside a cavity of its own calcified shell, surrounded by an entire world's worth of rock. We could only see it through the vibrations it caused, the way the seismic waves bent and slowed and reflected when they encountered its body. A ghost image, a shadow in the data, but the shadow had detail. The body was approximately 700 kilometers in its longest dimension, curled, the segments compressed against each other, the tapered end tucked against the denser end. If it were to uncurl, to extend, to straighten, the full length would be significantly longer. Perhaps 1,500 kilometers, perhaps more. The data couldn't resolve the hypothetical extended form because the organism had never been extended, not in the 4.5 billion years that the moon had existed. It had been curled in this position for the entire history of the solar system. The segments were visible as density variations in the reconstruction, each segment slightly denser than the one beside it, separated by boundaries where the density dropped. The valleys between segments, the same structural pattern as the organism in the Mars script and the Jupiter script, but different in detail. This was not the same species. The segments suggested a body plan that was independently evolved, or perhaps ancestrally related across distances and timescales that made the word related meaningless. Each segment was approximately 40 to 60 kilometers across. The organism had no features the seismograph could resolve that corresponded to sensory organs. No eyes, no mouth, or at least nothing the data could identify as a mouth. The interior of each segment showed density variations suggesting internal structures, organs, cavities, systems. The organism was not solid. It was complex. It had biology. It had been alive long enough for the moon to form around it, and the November 8th displacement showed that it was alive still. The displacement, the event that had triggered the alarm and changed everything, was now interpretable. That one of the tapered anterior segments had shifted position. A limb, or the organism's equivalent of a limb, had moved 200 meters laterally in 1 second. After 4 billion years of absolute stillness, the first voluntary movement since before life existed on Earth. Before photosynthesis, before multicellular organisms, before anything on Earth had eyes or bones or a nervous system. This thing had already been old, already been dormant, already been sealed inside its shell, buried under accreting rock, waiting. And the pulse, 0.008 hertz, 125 seconds, was its heartbeat, measured by Apollo in 1972, measured by our sensors in 2026, unchanged for at least 60 years and probably for 4 billion. A resting heart rate maintained through geological time, through the bombardment that scarred the lunar surface with craters, through the tidal locking that fixed one face toward Earth, through every phase that every human who ever lived had looked up and seen reflected in the night sky. The pulse had been there. Beneath the craters, beneath the Maria, beneath the dust, a heartbeat. November 22nd, 2 weeks after the first displacement, the pulse was no longer stable. It had been 125 seconds per cycle when it appeared on November 9th. By November 22nd, it was 118 seconds. The organism's heart was beating faster, not dramatically, 7 seconds over 2 weeks. But the trend was linear and accelerating. If it continued at the current rate, the pulse would reach physiological rates, rates consistent with an active, awake metabolism rather than a dormant one, within months. The thermal data was changing too. The deep sensors couldn't measure the organism's temperature directly. It was separated from them by 740 kilometers of rock. But they could measure the temperature of the rock, and the rock was warming. The 740-kilometer boundary, the outer surface of the organism's calcified shell, was showing a thermal increase of 0.3 degrees Celsius over baseline. Tiny. But the baseline had been stable for 5 years. The organism was generating more heat. Its metabolism was increasing. The dormancy was ending. November 25th, the surface sensors detected something I had to verify 3 times before I reported it. Microfractures. The lunar crust, the rock above the organism, the 740 kilometers of natural geological material that lay between the cavity and the surface, was developing stress fractures. The seismograph recorded them as a series of very small, very shallow events, magnitude 0.5 to 1.2, barely above the noise floor. But they were new. They hadn't been there before November 8th, and they were propagating outward from the organism's position, from the deep interior toward the surface. The shell was cracking. Not the organism's calcified shell, the geological shell around it, the moon's crust, the rock that had formed over 4 billion years, that had been solid and stable and dead, was developing fractures under stress from below. Something inside was pushing outward. I ran the stress analysis. The fracture pattern was consistent with a pressure increase at depth, the organism's body expanding fractionally as it warmed, as its metabolism increased, pressing outward against the cavity walls, which pressed outward against the overlying rock, that which had been under equilibrium for billions of years and was now experiencing stress it had never been designed, never been formed, to withstand. I brought the data to Vasquez. She read it again. Then she said something I wasn't expecting. She said, "It's stretching." I said, "The stress analysis suggests expansion." "Yes." She said, "No, it's stretching. The way something stretches when it wakes up." She said it with a flatness that contained something I recognized from my own voice in the weeks since November 8th. The flatness of someone who has accepted something that the mind was not built to accept. We were orbiting 110 kilometers above the surface of a body that was not a dead rock but a shell, a cocoon, an egg, a prison, containing something ancient and vast that was beginning, for the first time in 4 billion years, to move. Then I went to the cupola. I needed to look. The moon was below me, passing beneath the station at 6,000 kilometers per hour, the surface scrolling, craters and mountains and plains and the gray, dead dust that 8 billion people called moonlight when it reflected off this surface and fell on their faces at night. I looked at the craters, Copernicus, Tycho, Imbrium, the great basins, the impact scars from bombardments that had shaped the surface over eons. And I thought about what those impacts had done to the thing inside. 4 billion years of rocks hitting the outside of your shell while you sleep. The bombardment that created the Imbrium Basin, one of the largest impact events in lunar history, had driven a projectile deep into the crust. Had it reached the organism? Had it cracked the cavity wall? Had the organism felt it, the way a sleeping person feels a noise in another room, registering it without waking? I looked at the surface, and I saw it differently. The way the craters overlapped, the way the Maria, the dark flat plains of ancient basalt, were distributed almost exclusively on the near side, the side facing Earth. The standard explanation was tidal heating. The near side's crust was thinner, allowing magma to reach the surface. But what if the near side's crust was thinner because the organism was closer to the surface on that side? What if the Maria, the seas that the early astronomers named, were places where impacts had penetrated closer to the cavity, and the organism's body heat had melted the surrounding rock, which then flooded the basins? What if every feature of the lunar surface, every crater, and every rill, every wrinkle ridge, was not just the result of geological process, but the interaction between geological process and the presence of something massive beneath? I was looking at the moon the way a doctor looks at an X-ray, seeing past the surface to the patient beneath, and the patient was stirring. On November 28th, I saw the crack, not on the instruments, with my eyes. Through the cupola during a dayside pass over the Imbrium Basin. A rill, a narrow channel on the surface, the kind of feature that the lunar geological maps attributed to ancient lava tubes or tectonic graben. Except this rail wasn't on any map. I'd memorized the surface features in my observation area over 9 months. This feature was new, 12 kilometers long, running roughly north-south across the Mare Imbrium, but narrow, maybe 200 meters wide, but deep. The shadows at this sun angle showed depth, not a surface feature, a crack in the crust, propagating from inside. The moon was developing stretch marks. December 1st. Earth Command broke their silence. The message came through the encrypted uplink at 0600 UTC, emergency recall. All 4 crew members were to prepare for immediate evacuation. A retrieval vehicle was inbound from Lunar Gateway, ETA 22 hours. All data was to be transferred to portable drives and carried by hand. All station systems were to be powered down except the sensor network, which would continue operating autonomously. The station was to be left in a tumble that was consistent with its cover story as a defunct satellite. We were never there. I spent those 22 hours in the sensor ops bay, copying data. The 5 years of seismic records, the full tomographic reconstruction, the displacement events, the pulse recordings, the thermal data, the microfracture analysis, the gravimetric profiles, the 3D model of the organism, the segmented shape curled in the moon's core, captured in seismic shadow. All of it, onto drives that I sealed in a case and carried on my person. I was not going to let this data disappear. The retrieval vehicle docked at 0400 UTC on December 2nd. We transferred. The vehicle separated from Sentinel Station. A brief thruster burn set the station tumbling, a dead satellite, spinning slowly, catching sunlight and releasing it, anonymous, unimportant, as if it had never been crewed, as if the data it had collected was irrelevant, as if the thing inside the moon was someone else's problem now. The vehicle swung around the moon for the transit to Gateway, the final orbit, the last time I would see the lunar surface from this altitude. I was in the vehicle's small viewport bay, watching the moon pass, dayside, the craters lit in harsh sunlight, shadows knife-sharp. And there, in the Imbrium Basin, the crack. 12 kilometers long, visible from 110 kilometers with the naked eye, a dark line across the bright gray surface like a pencil mark on paper, a fracture in the face of the moon that hadn't been there a month ago. I looked at the crack, and I thought about scale. The organism inside the moon was approximately 700 kilometers across in its curled state. The moon's diameter was 3,474 kilometers. The organism occupied approximately 20% of the moon's internal volume. If it uncurled, if it extended, if it stretched, and if it woke fully and tried to move, the shell that contained it was not going to hold. The moon was not built to contain something alive. It was built by accretion, by the random collection of debris around a gravitational seed, layer by layer, over millions of years. It was strong in the way that rock is strong, rigid, massive, unyielding. But rock is brittle, and the thing inside was not trying to break the shell. It was just stretching, the way something stretches when it's been still for too long. And the stretching was cracking the rock from the inside. I watched the crack in the Imbrium basin grow smaller as the vehicle accelerated away from the moon. Then the moon was a sphere again, then a disk, then a silver-white circle in the viewport, getting smaller. It was the same moon that humanity had watched from every culture and every continent for 100,000 years. Familiar, beautiful, cracked. They debriefed me at Gateway, then at Elio Station, then at a facility in Virginia that I was transported to in a vehicle with no windows. The debriefing lasted 19 days. I gave them everything: the data, the analysis, the reconstruction, the organism's seismic portrait. I answered every question. The questions were precise and technical and asked by people who already knew the answers. The debriefing wasn't about gathering information. It was about establishing what I knew so they could determine how much to classify. Everything. They classified everything: the seismic data, the tomographic reconstruction, the displacement events, the pulse, the microfracture analysis, the surface crack in Imbrium, the organism. All of it, classified at a level that made the original program classification look like a public bulletin board. I was given a separation agreement, a non-disclosure clause that would outlive me and extend to my heirs, a pension that was generous enough to make clear that its purpose was silence, not gratitude, and a recommendation that I pursue civilian research opportunities away from seismological fields. They didn't want me near seismographs anymore. I bought a cabin in Vermont, rural, the kind of place where the nearest neighbor is a mile away and the nights are dark enough to see the Milky Way. I don't teach, I don't publish. I consult occasionally, enough to maintain the fiction of a career. What I do mostly is what I did on Sentinel. I monitor. The Apollo seismic data is public. It's been public since the 1970s. Anyone can access it. Anyone can download the waveforms from the Apollo passive seismic experiments and look at the deep moonquake data and see the anomalous signals that a generation of scientists attributed to tidal stress and background noise. And if you know what to look for, if you filter for 0.008 Hertz, if you isolate the signal from the noise, if you apply the same algorithms I used on Sentinel to data that's been sitting in a public archive for 50 years, you can see it. The pulse, right there, in the public data, visible to anyone with a master's degree in seismology and the right filtering software. Nobody looks. Because nobody has a reason to look. Because the moon is a rock. Everyone knows the moon is a rock. It says so in every textbook, every encyclopedia, every classroom presentation, and every press release. The moon is a rock that formed 4.5 billion years ago from debris ejected by a giant impact, and it has a crust and a mantle and a small iron core, and it's dead. Tectonically dead. Biologically dead. Completely, utterly, reassuringly dead. Every Thursday evening, I open my laptop and I check the Apollo data. The old instruments are off. They've been off since 1977. But the waveforms they recorded are still there. And the patterns in those waveforms tell the same story that my 40 sensors told on Sentinel. Something inside the moon has a heartbeat. And on November 8th, 2021, something inside the moon moved for the first time in 4 billion years. 7 years now. I check on Thursdays. I check the Apollo data, and then I check the publicly accessible data from the more recent lunar missions. The Chinese Chang'e seismometers, the Indian Chandrayaan gravimeters, the ESA surface science packages. None of them are as sensitive as the Sentinel network. None of them are positioned to detect deep interior events with the resolution we had. But they're there, and they're recording. And if you filter the data correctly, if you know the frequency, if you know the depth, if you know what a heartbeat looks like when it's transmitted through 740 kilometers of rock, you can see it. The pulse is still there. And it's faster. When I left Sentinel in December 2021, the pulse was 118 seconds per cycle. The public instruments don't have the sensitivity to measure the frequency precisely, but the long baseline data, months of recording, and averaged and filtered, shows the trend. The pulse is accelerating by approximately 0.2 seconds per month, slow, steady, a heartbeat speeding up, the way a heart speeds up when the body is preparing to move. I don't know what happens when the pulse reaches a threshold. I don't know what threshold matters, whether it's 60 seconds per cycle or 30 or 10, or whether the organism operates on a scale where any threshold I can imagine is irrelevant. I don't know what happens to the moon when the thing inside it wakes up fully. Whether the shell holds, whether the cracks propagate to the surface and the moon fractures and whatever is inside emerges into the light for the first time since before the solar system had planets. Whether the tides change, whether the orbit changes, whether the moon, our moon, Earth's moon, the silver disk that governs the tides and the calendars and the myths of every civilization that has ever existed, cracks open like an egg and reveals what has been hiding inside it for 4.5 billion years. I don't know. What I know is the data, the pulse, the acceleration, the displacement, the cracks. What I know is that something inside the moon moved in November 2021, and it hasn't stopped. It's moved 5 more times since. I can see the signatures in the public data, small events, easily dismissed as moonquakes, easily classified as tidal stress. But I know what they are. They're an organism stretching, waking up, adjusting position inside a shell that is starting to feel too small. And every Thursday, after I've checked the data, I close my laptop and I walk outside. My cabin faces east. On clear nights, and in Vermont in winter, the nights are very clear. The moon is there, rising over the trees, full or half or crescent depending on the phase, silver white. The same moon that the first humans saw when they walked out of Africa. The same moon that the Apollo astronauts walked on. The same moon that children point at and that poets write about and that 8 billion people sleep beneath every night without ever wondering what's inside. I stand in my yard and I look at it and I feel the distance, 384,400 kilometers of vacuum between me and that silver surface, and I think about the 740 kilometers of rock beneath the surface, and the 30 kilometers of calcified shell beneath that, and the organism curled in the dark at the center, 700 kilometers of ancient segmented body compressed into a sphere, pulsing, warming, stretching, waking. And I think about the crack in the Imbrium Basin, 12 kilometers, visible from orbit, and I wonder whether on a clear night with a good telescope you could see it from here, whether the crack has grown, whether new ones have appeared, whether the surface of the moon, the face that billions of people look at without seeing, has started to change in ways that someone will eventually notice and not be able to explain. And I wonder how long the shell holds, and I wonder what comes out. And I go back inside and I close the door, and I leave the moon where it's always been, in the sky, above the trees, silver and silent and beautiful. And I try to sleep beneath it, the way I've slept beneath it every night of my life, the way every human has slept beneath it since the beginning. But I don't sleep well anymore. Because I know what's inside, and every 113 seconds, a little faster now than last month, a little faster than the month before, it beats.